Let us begin lecture 14. As we have seen in last lecture that we can have a series which is also called standard reduction potential series for pure metals, where the condition is the ions of pure metals will reduce and there will be no other elements. Now, at the same time we have also noticed that some of the reduction processes like oxygen reduction or hydrogen reduction in case of water system, aqueous system, we can also have a concept of standard reduction potential. Like what we have calculated in case of this reaction, which is oxygen reduction in acidic medium, because you see we have hydrogen ion and there is no OH minus ion. So, that is what it is basically considered to be the reaction happening in acid medium or the pH when the pH is less than 7, and we got this value. Now, if we try to write standard this Nernst equation for this reaction, so we can have a Nernst equation plus RT NF, since N is 4 here. So, I can write 4 ln activity of ox. Now, here ox is the entire the top part. So, this entire thing becomes my ox. So, this is O2 or activity of O2 I can write in terms of pressure and activity of H plus 4 to the power 4 and activity of H2O, which is the reductant. Now, if we maintain this is to be 1 and this is to be 1 as well as this is to be 1, then we get this standard reduction potential for this reaction. Now, if we keep maintaining PO2 equal to 1 and H2 if we consider to be pure and it is in a liquid. So, then still we can consider activity H2 equal to 1, then this equation becomes E0 O2 plus, and if it is standard state, that means RT by F, it becomes 0.0591. We have already calculated, because I calculated this 314 into 298 divided by 96500, it goes to 0.09591. So, by 4 ln, so that time into 2.303. So, we are considering the log conversion. So, this becomes my log activity of H plus 4. So, this becomes E0 O2 2H2O plus 0.0591 into log of activity of H plus. Now, I can, if it is ideal system, so I can write E0 O2 2H2O minus 0.0591 pH. So, here log minus H plus equal to pH, and we have also considered the ideal solution. So, activity of H plus equal to concentration of H plus, where activity coefficient equal to 1. So, that case we get this equation. So, similarly, so this equation will be very critical when we try to find out the stability of a particular metal in aqueous system. The stability in the sense that whether in, for example, what a metal is dipped in water of certain pH, whether that metal would dissolve or it would not at all dissolve, or it would dissolve initially and then finally it will passivate. All three conditions can be judged from a diagram which is called pore bed diagram, that while drawing that pore bed diagram, this equation would be very critical. Now, coming to, so now if we try to see the other reaction, O2 plus 2H2O plus 4E equal to 4OH minus, this is another reduction reaction. Here also we can calculate delta Z0 equal to mu 0 OH minus minus mu 0, sorry, this is 4 and minus mu 0 O2. So, this is 0 as per our convention, because at standard state oxygen chemical potential of pure oxygen is 0. So, this we can calculate 4 into mu OH minus equal to minus 157.1 joule per mole, and we know mu 0 H2 equal to minus 236,964.2 joule per mole. So, then this becomes minus 157,147.1 minus 2 into minus 236,964.2. So, this becomes, if I try to find out those values, so 2 into 236,964.2 equal to plus 473,928.4 minus 4 into 157,147.1 628,588.4. So, this minus 928.4 equal to minus 154,660. So, this is equal to nothing but minus NF E0 O2 OH minus. So, E0 N equal to 4 here. So, E0 equal to 154,660 divided by 4 into 96500 equal to 0.401 volt. So, this is 4 OH minus. So, because this is my reductant, this is my oxidant. So, we get this, and also if we try to write the Nernst equation, so we can write RT by 4F ln activity. Instead of activity, in case of oxygen we can write PO2, then we can write activity of H2O 2 divided by activity of OH minus 4 to the power 4. So, this we can simplify. If we simplify this part only, so this part becomes 0.0591 by 4. So, this is 1, this is we keep it 1, and when this activity of OH minus is also 1, then this becomes this. This potential of the cell becomes, half cell becomes the standard reduction potential. So, now if this is not equal to 1, then we can have, and if it is a dilute solution, because in the dilute solution ideality can be maintained. So, then log 1 by 4. So, this we can write it as 0.0591 by 4 into 4 log 1 by OH minus. So, I can still write it like 0.0591 minus log of OH minus, or I can write POH, since the definition of POH equal to minus log of OH minus 1. This is the definition. So, I can write this. So, this equation becomes EO2 for OH minus equal to E0 O2 for OH minus plus 0.0591 POH. Now, if I consider H2O, the water, I can write this, the dissociation of water, and in that case we can write the dissociation constant is nothing but 10 to the power minus 14. So, that case I can write delta G equal to minus RT ln K. Okay, so, I can write this when the system reaches equilibrium, and since K is 10 to the minus 14. So, I can write activity in terms of concentration, if I would like to write H plus OH minus equal to divided by H2O equal to 10 to the power minus 14. Now, if I take logarithm of this, so log H plus log OH minus equal to minus 14, which I can write in the form of pH plus POH equal to minus 14. Since this is nothing but minus pH, this is nothing but minus POH. So, this POH becomes 14 minus pH. So, we have this reaction equation. So, I can start with this, since pH equal to 14 minus POH, and also we know O2 4 OH minus equal to E0 O2 4 OH minus plus 0.0591 POH would be equal to E0 O2 4 OH minus plus 0.0591 14 minus pH equal to, this value is, as we have calculated, 0.401 plus 0.0591 into 14 minus 0.591 pH. So, if I try to find out this value, so 0.0591 into 14 equal to 401 plus 0.827 minus 591 pH equal to 8212 minus so we get this, which is, if we try to compare the value what we have obtained here in this case. So, this is the reaction number where acidic media, so which I can write it as 1.227 minus 0.0591 pH. So, that means I can see that this is for this reaction, and if I try to see now, you could see that these two reactions are almost similar with a little bit difference on the third digit after decimal, but this difference is not going to be there if we take exact value of all the parameters for calculating this quantity or this quantity. Okay. So, finally, we can say that these are equivalent reactions. I can say equivalent reactions. For example, let us say I would like to plot them on pH versus E0, sorry, E potential or the reduction potential. Now, when pH is equal to 0, both the potentials are almost on the same point. This is this and this is this. So, those both are on the same point, and the slope of the reaction is nothing but this is the slope minus 0.0591. So, and if this is my 7, so if I try to extend this 7 pH, so I know that this reaction happens when pH is less than 7. So, then up to that, if we extend this, this is the slope is minus 0.0591 with the pH. So, this reaction happen over this plot. Now, in the basic medium, because it involves OH minus, and also in the neutral case, these reactions happens. So, that time the plot would be, and if we see this particular region where we can also see that this this reaction, this particular plot for these reactions, it is also on the same line, because this would be lying on the same plot and then it will be extending. So, this reaction happens in this zone, but actually they are lying on the same line. Only difference is oxygen reduction in acidic medium happens when pH is less than 7, and oxygen reduction in basic or neutral medium happens when pH equal to 7 or greater than 7. So, these happens when pH 7 and these happens pH less than 7. So, this is the only difference, but they are falling on the same plot. Now, my interest is, now you see that here also we can find a reduction, standard reduction potential, and in the previous case also we could find the standard reduction potential. Here is this one. This is the standard reduction potential for the oxygen reduction in acidic medium. So, this particular diagram will come again for discussion when we start talking about Pobe diagram, but from this at least we are clear that both the reactions are falling on the same slope line. Now, if we have to see the another reaction which is 2H2O plus 2E equal to H2 plus 2OH minus, this is also a reaction in aqueous medium. Here also we can calculate E0. That time this would be, I can say that this is H2. So, this is the reduction process, because this is reduction I can calculate this. So, how do I calculate? Again I have to find out delta Z0 equal to mu 0 H2 plus 2 mu 0 OH minus minus mu 0 2 H2O. So, I can put those values, this is 0 plus 2 minus 157 147.1 plus 2 into 236 964.2. So, I can calculate this value. So, this becomes 236,964.2 minus, so this becomes minus plus 159,634.2, which is equal to minus NF E0 H2, N equal to here 4, 2. So, this is the 2 electrons. So, E0 equal to 159,634.2 by 2 into 96500 equal to minus 0.827 volt. Now, if I write it in terms of Nernst equation, now here this particular part we can simplify. So, this becomes 0.0591 by 2. So, this is 1 atmosphere if we maintain that, and if this goes to OH minus square, so that means in the dilute solution and also ideality is maintained, then this goes to log OH minus whole 2, which is 0.0591 POH with a minus sign. With a minus sign, definitely yes. So this becomes 0.0591 by 2 into 2 log OH minus ion. So this PaOH. And now again I can have POH equal to 14 minus pH. So then I can write okay. So here we see that we have committed a mistake, because here we have put the aux here. Actually aux should be here and this part should be here. So in order to write it again, so I can cancel it, I can cancel this part and write RT2F ln AH2O pH2. So now this goes to 1 and this I can write it as OH minus square. So everything is all right, only thing is I have to put a minus sign here. So then it becomes plus, because this was done with reference to this numerator and denominator would be exchanged. So this becomes minus and finally it becomes plus POH. So then I can write 14 minus pH. So E equal to 2H2O, H2 equal to E0 2H2H2 plus 0.0591 into 14 minus 0.591 pH. So this is minus 0.827. We have also calculated before, this is 0.827 minus 0.0591 pH. So this, so finally this becomes minus 0.0591 pH. Sorry, not this. Now you see this relation, and for this, what was the relation? So these are also similar. So it means that this reaction and this reaction, they will also fall on the same line with the same slope, but one equation would be valid for in case of acidic medium, another equation would be valid for basic medium. This would be basic or neutral, this would be valid when pH greater than equal to 7, and this would be valid when pH less than 7. So we stop here. We will continue our discussion on these equations and then standard reduction potentials in our next lecture. Thank you.